The universe is vast and mysterious, and its origins have puzzled scientists for centuries. But thanks to modern technology and scientific advancements, we now have a better understanding of how the universe came into existence. In this video, we will explore the chemistry of the Big Bang, the event that gave birth to the universe as we know it. A cosmic background with stars and galaxies. The Big Bang theory suggests that the universe began as a singularity, a point of infinite density and temperature. About 13.8 billion years ago, this singularity expanded rapidly, creating space, time, and matter. But how did this happen? To understand the chemistry of the Big Bang, we need to look at the fundamental building blocks of matter: atoms. A zoom-in shot of an atom. Atoms are made up of protons, neutrons, and electrons. Protons and neutrons are found in the nucleus of an atom, while electrons orbit around the nucleus. These particles are held together by the strong nuclear force, which is one of the four fundamental forces of nature. An animation of protons, neutrons, and electrons. But where did these particles come from? According to the Big Bang theory, they were created in the first few minutes after the Big Bang. Let's take a closer look at what happened during this time. An animation of the Big Bang. At the beginning of the Big Bang, the universe was extremely hot and dense. As it expanded, it cooled down, allowing protons and neutrons to form. However, these particles were not stable yet. They were constantly colliding with each other, creating new particles and breaking apart. An animation of particles colliding and breaking apart. This process continued for about 3 minutes until the universe had cooled down enough for protons and neutrons to combine and form the nuclei of atoms. But there were no electrons yet to orbit around these nuclei. This is where another important event comes into play: recombination. An animation of recombination. Recombination occurred about 380,000 years after the Big Bang. At this point, the universe had cooled down enough for electrons to combine with nuclei and form atoms. This process released a tremendous amount of energy in the form of light, which is known as the cosmic microwave background radiation. An animation of atoms forming and releasing energy. This radiation can still be detected today, and it provides evidence for the Big Bang theory. But there is still much we don't know about the chemistry of the Big Bang. In the next segment, we will explore the role of dark matter and dark energy in the universe. The universe is made up of matter and energy, but there are two mysterious components that make up the majority of the universe: dark matter and dark energy. These components cannot be seen or detected directly, but their effects can be observed through their gravitational influence on visible matter. An animation of the universe with visible matter and dark matter. Dark matter is believed to make up about 27% of the universe. It is called dark because it does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be inferred through its gravitational effects on visible matter. An animation of the gravitational effects of dark matter. Dark matter is thought to have played a crucial role in the formation of galaxies and other large structures in the universe. Without its gravitational influence, visible matter would not have been able to clump together and form these structures. An animation of galaxy formation. But what is dark matter made of? Scientists are still trying to answer this question, but they believe that it is made up of particles that interact weakly with other matter. These particles are known as WIMPs, or weakly interacting massive particles. An animation of WIMPs. Dark energy, on the other hand, is believed to make up about 68% of the universe. It is even more mysterious than dark matter, as its nature is not well understood. Dark energy is thought to be responsible for the accelerating expansion of the universe, which was discovered in the late 1990s. An animation of the accelerating expansion of the universe. The discovery of dark energy was a major breakthrough in our understanding of the universe, but it also raised new questions. What is dark energy made of? How does it interact with other matter? These are questions that scientists are still trying to answer. An animation of scientists studying dark energy. The study of dark matter and dark energy is an active area of research, and scientists are using a variety of techniques to try to understand these mysterious components of the universe. In the next segment, we will explore the role of hydrogen in the universe. Hydrogen is the most abundant element in the universe, making up about 75% of its mass. It is also the simplest element, consisting of just one proton and one electron. But despite its simplicity, hydrogen plays a crucial role in the formation of stars. An animation of hydrogen atoms. In the early universe, hydrogen gas was distributed almost uniformly throughout space. However, small fluctuations in density eventually led to the formation of clumps of gas that were dense enough to collapse under their own gravity. An animation of gas clumps collapsing. As these clumps collapsed, they became hotter and denser, eventually reaching temperatures and pressures high enough to initiate nuclear fusion. This process releases a tremendous amount of energy in the form of light and heat, causing the gas to glow and become a star. An animation of nuclear fusion and the formation of a star. The energy released by nuclear fusion also creates a pressure that counteracts the force of gravity, preventing the star from collapsing further. This balance between gravity and pressure determines the size and lifespan of the star. An animation of the balance between gravity and pressure. Small stars, like our Sun, burn hydrogen slowly and steadily for billions of years before eventually running out of fuel and collapsing into a white dwarf. Larger stars, on the other hand, burn hydrogen much more quickly and violently, eventually exploding in a supernova and leaving behind a neutron star or black hole. An animation of the life cycle of a star. The formation and evolution of stars is a complex process that is still not fully understood. However, studying the chemistry of hydrogen and other elements in stars can provide valuable insights into the history and evolution of the universe. An animation of scientists studying stars. In the next segment, we will explore the role of heavier elements in the universe and how they are created in the hearts of stars. While hydrogen is the most abundant element in the universe, heavier elements like carbon, oxygen, and iron are also crucial for the formation of planets, life, and even the universe itself. But where do these elements come from? The answer lies in the hearts of stars. Animation of a star's interior. Inside a star, nuclear fusion reactions convert hydrogen into helium, releasing energy in the process. As the star ages and runs out of hydrogen, it begins to fuse helium into heavier elements like carbon and oxygen. An animation of nuclear fusion in a star. But the fusion of helium into heavier elements requires much higher temperatures and pressures than the fusion of hydrogen. This means that only the most massive stars are capable of producing elements heavier than carbon and oxygen. An animation of the fusion of helium into heavier elements. When these massive stars eventually run out of fuel, they undergo a catastrophic explosion known as a supernova. This explosion releases a tremendous amount of energy and scatters the heavy elements produced in the star's core throughout the universe. An animation of a supernova explosion. These heavy elements then become incorporated into new stars, planets, and even life. In fact, every atom in our bodies and in the world around us was created in the hearts of stars. An animation of atoms being created in stars. The study of how elements are created in stars is known as stellar nucleosynthesis, and it is a crucial area of research in astrophysics. By studying the chemical composition of stars and the elements they produce, scientists can learn more about the history and evolution of the universe. An animation of scientists studying stars. In the final segment, we will summarize what we have learned about the chemistry of the Big Bang and its role in the universe.